Hello student, welcome to all of you in the next physics lecture. Now we have to see here the video number 44 and chapter number 6, the superposition of the waves. Now we have to see here the next point, the vibration of the air column, a pipe open at the both end. In previous lecture we have to see the vibration of air column, pipe closed at one end. But here we have to see here the vibration of air column, pipe open at both end. Then first we have to draw the diagram for the vibration of air column, pipe open at the both ends. This is the diagram, first, second and third. You have to also write figure A, B and C. Then this both end of that air column of this pipe are these are the open. This pipe should be open at the both ends. Then this vibration of air column, which is as shown in figure, when the stationary waves are the set up in this pipe, which is open at the both end, they have to obey the boundary condition in such a way that they obey the boundary condition that there must be the antinodes at its open end. When the pipe is closed at one end, then there must be the node must be at the close end and antinode must be at the open end. But here the pipe is open at both ends, therefore we have to boundary condition we have to consider that there must be antinode at its open end. That means both end they are the open, therefore there should be antinode at its open end. Then the different modes of vibration of the air column in a pipe open at the both end is as shown in figure first, second, third, or the figure ABC. In this first figure, this is the fundamental mode of vibration, and this vibration of air column is as shown in figure A. Now the lambda and the is the wavelength and the L is the length of this air column. L is the length of air column and the lambda is the wavelength. Then we have to consider the length of air column by using these properties of the stationary waves. The distance between antinode to antinode is nothing but what? This is nothing but the lambda by 2. Therefore, L is equal to lambda by 2. I have to write here. We follow these conditions. Distance between the two successive node or antinode is equal to lambda by 2, or the distance between two node or adjacent antinode is equal to lambda by 4. By using this, we can write here the length of air column from antinode to antinode. This L is equal to lambda by 2. Then the corresponding frequency of vibration, that is the fundamental mode of vibration, which is given by n is equal to v upon lambda. We can write from this relation, we know that the v is equal to n lambda, therefore n is equal to v upon lambda. Then substituting this value, L is equal to lambda by 2, therefore lambda is equal to, we have to write here twice L. This length of air column here, this length of air column, we have to write antinode to antinode, L is equal to lambda by 2. Therefore lambda is equal to twice L, and substituting this value, lambda is equal to twice L in this equation, n is equal to v upon lambda. Instead of lambda, we have to substitute the twice L, therefore n is equal to v upon twice L. This is the lowest frequency with which the air column can vibrate, so that it is called as a fundamental frequency. N is equal to v upon twice L. In pipe closed at one end, this formula is, you know that n is equal to v upon 4L. Okay, and in this pipe open at the both end, this fundamental frequency n is equal to v upon twice L, because this length of air column is lambda by 2, therefore lambda is equal to twice L, and we know that corresponding frequency of vibration n is equal to v upon lambda, and lambda is twice L. Substituting this, n is equal to v upon twice L, and this is the lowest frequency with which the air column can be vibrate, called as a fundamental frequency. This is known as a fundamental frequency. N is equal to V upon twice L. Then again, the next mode of the vibration is as shown in figure B. This is the second figure. Again, we have to see here the second figure. This is the second mode of vibration. Then for draw the diagram, when we can use the tricks, when the pipe is open at the both ends, then we have to remember here this diagram is half half, one and half, and two and half. Again, see here, to trick is here to draw the diagram for this pipe open at the both ends. We have to, this both sides are open, then there are antinode are must essential. These antinodes are must be provide this at the open end of this pipe. Therefore, the half and half first, then one and half, then two and half. That means antinodes are at its open end. Then second, next mode of vibration is as shown in figure B. And here N1 and lambda 1 be the corresponding frequency and the wavelength and the length of air column which is given by. We have to see here the length of air column. Distance between antinode to antinode lambda by 2, and again distance between antinode to antinode lambda by 2. Then lambda by 2 plus lambda by 2, lambda, complete lambda. Okay. Therefore, this length is equal to lambda 1. This is the next mode. Therefore, we have to write lambda 1. L is equal to lambda 1. Then how it can we find out the corresponding frequency? Then corresponding frequency of vibration is nothing but N1 is equal to V upon lambda 1. Then lambda 1 length is what? Length L is equal to lambda 1, or lambda 1 is equal to, we have to write here L. Then substituting here, N1 is equal to V upon L. Okay. Lambda 1, instead of lambda 1 we can substitute the L, length of air column. And therefore, this equation we have to multiply by 2 and divide by 2. Then this N1 is equal to this 2 into V upon twice L. 2 into V upon twice L. We have adjust here this term V upon twice L, because the V upon twice L is nothing but what? This is the fundamental frequency of mode of vibration. Instead of this V upon 2L, we can write the N, and therefore substituting this V upon twice L N, N1 is equal to twice N. N1 is equal to twice N. This is the next mode of vibration, which N1 is equal to twice N. Again, we have to also find out the third mode of harmonic. How it can we find out? Then there are the two complete waves and half, two and half, one and half, and two and half. Then again, by using this boundary condition, the antinodes are at its open end. It must be antinodes are at its open end. Therefore, this distance between antinode to antinode lambda by 2. Again antinode to antinode lambda by 2. Again antinode to antinode lambda by 2. That is the 3 times lambda by 2. Therefore, length of air column L is equal to 3 lambda 2 by 2, because antinode to antinode, antinode to antinode, antinode to antinode 3 times lambda by 2. Therefore, length of air column here we have to also write L is equal to 3 lambda by, this is the third mode of vibration. We have to write here lambda 2 and upon 2. Okay. Then value of lambda 2 we have to write here 2L upon 3. To take this side, 2L upon 3. Okay. Then corresponding frequency of vibration is nothing but what? N2, and N2 is equal to V upon lambda 2. Again substitute the lambda 2 twice L upon 3. Then we get N2 is equal to V upon lambda 2. Value of lambda 2 is what? Twice L upon 3. Then this twice and 3 we take this numerator side. Again this V upon 2L is nothing but what? N. Therefore, N2 is equal to, we can write here 3N. And this is the next mode of vibration. N2 is equal to thrice N, or also called N1 is equal to twice N, N2 is equal to thrice N. Similarly, we also write here N3 is equal to 4N, 5N, 6N, 7N, so on. In this way, the vibration of air column, pipe open at both ends, is consist of the fundamental frequency, that is n is equal to V upon twice L. Fundamental frequency n is equal to V upon twice L along with all the harmonics. That means twice n, thrice n, 4n, dot dot, so on. This vibration of air column pipe open at the both end is consist of fundamental frequency, that is n V upon twice L, and along with all the harmonics. This is nothing but the vibration of air column pipe open at the both end. You have to understand well. Okay, stop here. Thank you.